4 ties in what we've been dealing with in actual bonds, so covalent and ionic bonds, and what are called intermolecular forces. And intermolecular forces are what keep molecules near to one another but don't actually bond them. So picture in your head right now, and keep this image in your head for the remainder of the lesson. An intermolecular force is if what holds, let's say, a cup of water, keeps all of the water molecules in there together. It doesn't bond the water molecules to one another, but it's holding them in the cup so that they don't go flying off into space as just single molecules of water. So with that in mind, let's look first at the difference between two important words that deal with these two things. And those would be intermolecular forces versus intramolecular forces. And so this is tying together what we had talked about before, intramolecular, or those bonds, and this new word, intermolecular, the things that are holding bonded molecules together. So first of all, intermolecular forces between molecules, again, not actual bonds within a molecule, but the forces that are between molecules that help them to interact. And the different types of intermolecular forces we have are called dipole-dipole forces, hydrogen bonding, London dispersion forces, which are also called van der Waals forces. And these are weak forces in comparison to actual bonds. So what's holding my water molecules together in my cup are weak compared to the actual bonds that hold the hydrogen to the oxygen together with that sharing of electrons. Intramolecular forces are the forces within a molecule. So I'm looking at my one water molecule now, that bond between the hydrogen and the oxygen, that's called my intramolecular force. And so we call these our actual bonds. And we have covalent, polar covalent, and ionic bonds. These are much stronger forces than the intermolecular forces. So let's look at each of these intermolecular forces, these forces that are holding molecules near one another but not bonding them. And the first one is called London dispersion forces. So molecules are attracted together due to the induced dipoles in their electron clouds. So we have something that's nonpolar, something that I have, let's say, chlorine gas. What's keeping the chlorine gas molecules near one another when they would generally just repel one another, not interact at all? Well, as one comes close to another one, it interacts with the electron clouds that are around it and pushes them one way or another. Imagine a magnet. As you get one magnet closer to the other, it's going to move it around. If you put the like sides by one another, it would start moving around on your table. That's the sort of image that we have here. This is the weakest of the intermolecular forces because it happens in just an instance. It's just a momentary induced dipole, very moment where we have one side of it being partially positive and one part of it being partially negative for just a moment as those electron clouds interact. All molecules experience this force at some point in some manner, but some also engage in other forces as well. Again, we said London dispersion is also often called van der Waals forces. I believe the IB Bio curriculum uses the van der Waals forces more, while the chemistry curriculum, the new guide that we're under, is saying London dispersion. So know that those two are used interchangeably. For noble gases and nonpolar molecules, this is the only type of intermolecular force that they undergo because they don't have dipoles in general unless we have that momentary interaction between them inducing a dipole. Here's an image of it. So I have two helium atoms that come close to one another. As they come closer to one another, the electrons of the one atom are going to be attracted towards the proton or the nucleus of the other one. That nuclear charge, that effective nuclear charge, is going to be pulling or attracting those two slightly. And so as it pulls that in, we have a momentary negative in this direction, but that's going to push these electrons further away. So we have our positive here being attracted to the negatives of this atom, but it's just for a second, and then they're going to shift back around, and it's going to go back to the way that it had been. So my positive nucleus is going to be a partial positive. My negatives that were getting attracted are my partial negative, and since they were attracted, the negatives on my electrons on this atom are getting pushed away because we know that sames repel one another. So I have a partial negative there. And again, it's happening quickly, momentarily, and then it goes back to normal, or it interacts with another one that's nearby. Okay, dipole-dipole forces are stronger than van der Waals or London dispersion forces, and they are the traction between the partially positive end and one polar molecule and the partially negative end of another polar molecule. The molecules will arrange themselves to maximize the attraction and minimize the repulsion forces. And the further apart they get, the weaker these attractions are. And again, you can imagine a magnet with a positive and a negative side. The further apart you pull them, the weaker the magnetism is between them. Here's an image of it. So these are just molecules that have a positive end and a negative end, or a partially positive end and partially negative end, not momentarily, but always have this charge. Hydrogen iodide would have been one of our examples, or with the hydrogen is the partial positive and the iodine is the partial negative because it's more electronegative. And so we just see these dotted lines representing where things are going to repel, like the negative and the negative, and where they're going to attract, like the positive, positive. And then we get to our strongest of the intermolecular force, and I hate this one because it's called hydrogen bonding, but we're not actually talking about an intramolecular force that we would call a bond. We're not talking about that. We're talking about the intermolecular force, or the forces between molecules. And we don't want to get that confused, and that is such a misnomer in my mind that they would name this bonding. Because that's not what an intermolecular force is. It's the attraction between molecules, not the attraction within a molecule. So with hydrogen bonding, this is a special type of dipole-dipole force, and the reason it's special is because it's so much stronger. It requires, here's where the bond part comes in, so I know where they're getting it. I just don't like that they're using that term. The hydrogen, we have to have a hydrogen, and that hydrogen has to be bonded in a molecule to a very electronegative element, and that's either going to be nitrogen, oxygen, or fluorine. And so a way to remember it is I can't get enough NOF of hydrogen bonding, or hydrogen bonding is almost fun, F-O-N. Those are two that previous students have come up with to remember that hydrogen bonding must include a bond within the molecule. So we're talking intramolecular force. We have to have hydrogen bonded to one of these three, like water. Water, we have hydrogen bonded to oxygen. So I have an actual intramolecular force between hydrogen and oxygen. But what I'm talking about with hydrogen bonding is the intermolecular force. So going back to that image in our mind about a cup filled with water, the intermolecular force that's occurring here, the force between the molecules, is called hydrogen bonding. That's what's holding them so close to one another. This is the strongest of the intermolecular forces, but it's still much weaker than intramolecular forces. It's not a bond. It's not holding elements within an atom together. It's just what's holding molecules near to one another. And here's our water example. So I have oxygen with 2 hydrogen. They're going to do the same thing that the dipole-dipole did, where they arrange themselves with the positive, increasing attraction and decreasing repulsion forces. And so they just arrange themselves in such a way that we can have an overall attraction. So if we want to think about which forces we're working with, we first of all ask ourselves, or we're looking at molecules or ions, we ask ourselves if there are ions involved. If yes, there are, then we ask ourselves, are polar molecules and ions both present? If it is, we would call that an ion dipole force. And examples would be potassium bromide and water as an example. But we also have water showing up here as hydrogen bonded to nitrogen, oxygen, and fluorine, where we have a polar molecule. So we can see some of them show up in multiple places. If we don't have polar molecules, but we just have ions, then I have an ionic bond, like sodium chloride. If I have no polar molecules involved, then those are my London dispersion, or my London forces. And all of these are falling roughly under van der Waals forces. So how do intermolecular forces impact physical properties? First of all, we have volatility, so how reactive things are, how much they're going to all of a sudden burst into flames, that sort of thing. A weak intermolecular force makes it easier for molecules to break away from one another and therefore vaporize. So if I have something like methanol that has some weak interactions, they're going to start breaking away easier, which is why when we light that on fire, it's going to react more violently. With solubility also, if we have greater intermolecular forces between the solute and the solvent, we're going to have a higher